thanks for the opportunity to talk in this transparent PV workshop. Before showing any data, thanks for Professor Lang to being able to bring this standardized protocols for measurements and including this assessment criteria. I have to say from our laboratory, we do not have a sputtering machine for transparent contact to be reported. So our reporting transparency data are based on this active layer, and this PV data are using the same active layer, but being coated with the reflective gold back contact. So this is I need to clarify this before starting my presentation. Yeah. So for this point, it's for this point of work package 2, impressive exactly development of this UV or near UV perovskite, so that we can produce high voltage with a good efficiency output. Yeah. So while large bandgap photovoltaic cells, there are a couple of applications, including tandem cells that we are going to use, and also transparent photovoltaic and solar field applications. And for transparent photovoltaic, the first approach might come from the narrowing this absorption band from whole width for region to UV or near UV part. And second approach is to reduce the thickness of the photoactive layer, so that to let pass more light through the photovoltaic cell. So while perovskite, as mentioned, perovskite materials have ultra good flexibility between the optoelectrical behaviors or properties from UV until far, or not far, but IR region from like 400 nanometer to until over 1000. Yeah, and these are pretty much easy to be solution processable, and together it can also produce very high efficiency. So it is no longer a trademark between the cost and efficient for perovskite. Yeah. So for transparent perovskite photovoltaic are still this kind of two approaches. The first is to reduce the absorption band to UV or near UV part, and second is to reduce the light pass through the perovskite. So first, I will quickly talk about the first part. During our optimization, we do realize that we do not get higher voltage upon reducing the absorption band, that is increase the band gap until 2.3 electron volt, which is corresponding to the pure MAPB-BR3 perovskite. Because of the phase issue, we cannot get higher voltage, thus not higher efficiency at bromide plus chloride blend perovskite. So we focus initially on MAPB-BR3 based perovskite, and with a couple of intensive optimizations like solution processing engineering and post-treatment and new HTMs, thanks to the help from UNITO, we are able to get outstanding VOC over 1.65 millivolt, and recently we even get 1.67, which is considered to be the record VOC for single junction perovskite photovoltaic cells. And in addition to VOC, we have to emphasize that the outputting power is as well important. So to improve it, we need to get a higher perovskite film quality. Yeah. As we know, this MAPB-BR3 based perovskite have very fast crystallization speed during solution processing technique. So this will inevitably create problem, including defects, bulk defects, and surface defects, and this kind of together with this kind of pinholes within the perovskite film. And we introduced firstly to use post-vapor treatment with methylamine gas. And with this methylamine gas, the perovskite will form an intermediate like a semi-liquid phase. So this semi-liquid phase will heal this pre-existing pinholes on the top of the film and within the perovskite. And we can see from the right part of this cross section and top view figures. The quality of this pure bromide MAPB-BR3 based perovskite has been significantly improved after we treat this perovskite film with methylamine gas, and these pinholes are substantially disappeared after treatment. And well, as I also mentioned, with this MAPBBR3 perovskite, because of this polycrystalline nature and solution processing technique, surface defects is also one of the intensive problems that is causing the poor efficiency of this kind of cell. So we introduce a newly developed surface passivation agent, which is neopentan ammonium chloride, to apply on the surface of this MAPBBR3 perovskite. And we realized that this surface passivation agent is forming a thin layer on top of the MAPBBR3 perovskite, forming with a thickness of roughly 5 nanometers. And this 5 nanometer thick surface layer will not change the perovskite morphology or crystallinity of the MAPBBR3. But if we can compare it from the top left figure, after MA treatment, the peak, okay, well, qualitatively, the peak has been significantly increased. We can also imply a better perovskite film quality upon this MA vapor treatment. But after MPACL, this does not alter. And next, we also perform these optical measurements toward this MA treatment plus surface treatment. We can see apparently with MA treatment, we can already improve the optical film quality of this pure bromine perovskite to we can already improve it, and with additionally surface coating with our MPACL passivator, we get even much better pure lifetime. So this can also be implied from this QY measurement. So with both MA vapor post treatment and surface coating with MPACL, we can realize much improved PRQY and suppressed VOC loss. And the VOC stability is also like improved with synergistically treatment with this MA vapor and MPACL. And next, well, considering the power output with our, again, this is of course not one-shot business. With our optimization, we realize the best performing cells are coming out with this combined MA vapor treatment plus this surface coating with the MPACL. We are able to get PCE around over 10%, and the current of the integrated current. I will mention here again, we use a reflective back contact coating. Is in a good agreement with IPC measurement for IPC measurement with this IV measurement. And the first 5 minutes MPP tracking of PCE prove good operational stability initially, and we show big potential on the improvement of the photovoltaic performance of pure bromine perovskite solar cell with simultaneously like MA vapor treatment plus surface coating. And stability is okay as well important. We do realize there might be a problem of polycrystalline and HTMs, but we, to our surprise, we observe pretty much good stability for this this combination between MA treatment and MPACL surface coating. If you see the top figure, this is exposing to ambient air without MPP. This we attribute this to the degradation that is induced by the humidity in the open air. We know spiral is hydrophobic, but the dopant there, like lithium TFSI and TPP, is kind of hydrophobic. But to prevent this to really damage, to prevent the air, the moisture in the air to really damage the perovskite active part, we attribute this improved stability against humidity to this hydrophobic nature of this new passivation material that is new MPACL. And the bottom figure, which is longer, okay, this is referring to MPP tracking stability with this MA and MPNCL treatment at 60 degree. we do understand that spiral will undergo like a glass transition over 60 degree, but in this system, it seems like this was not a big issue, really affecting the stability here. But in contrast, our control device without interlayer and with a relatively poor morphology without MA treatment decayed pretty much faster than exponential decay within the first 100 hours, and well, slowly decayed to like almost no efficiency compared to the initial. And going back to transparency, we do realize there's an improving in the absorption intensity after MA treatment. We attribute this to the, well, very likely to be existing pinhole scattering effect. So because if we see this absorption curve, we also see like a higher absorption intensity beyond the optical band gap. Yeah. So to verify this, we use a integration sphere to roll out the scattering effect, and we got completely like a identical absorption curve before and after MA treatment. That means there exists well, substantial amount of pinholes that can scatter the light, and that this will affect the, well, straight light path transparency. But here I also would like to mention that if we see the total transparency that is integrated, this should not give a difference just with the MA treatment and without MA treatment. Yeah. And to a short summary, we got a record efficiency for large bandgap perovskite solar cells over 10% at maintaining a high active layer transparency with AVT roughly 60%. Yeah. This was the active layer AVT and record VOC for single junction perovskite solar cell together with outstanding operational stability. And apart from this, I also would like to quickly go through this another approach to reduce the light pass through the photoactive materials with a flat band material. We call it panchromatic dyes. And this is not completely panchromatic because we see more intensive absorption for perovskite in shorter wavelength range. That is also why it appears to be yellowish. If we see the IPCE for fully assembled cell with enough thickness harvesting most of the photons, it is roughly okay in terms of harvesting or quantum conversion. It is kind of panchromatic. So we dilute the precursor solution to create a thinner perovskite solar cell with a pure iodide perovskite, hoping to get good transparency, maintaining good VOC. So this is roughly the result with reduced precursor solution. We need to get much improved like AVT, but we were not able to maintain a similar level of VOC. Might likely coming from this inhomogeneity, likely related to this rough surface that is creating a kind of shunt. Yeah. But anyway, with this 0.4 millimole precursor concentration, we managed to get like roughly over 60% active layer AVT with PCE over 6%. But I have to say here again, this is the active layer AVT. Yeah. And finally, thanks for your attention. This is you're welcome for questions.
Thank you, Yuhang. Any questions?
Yes, Frédéric. Yes, one question from my side. Just have one doubt. The transparency values you're reporting are of the absorber layer, the perovskite layer of the whole cell.
That's true. It's only the absorber layer because we want not to spot a transparent back contact to make this measurement. Otherwise, it's gonna be zero.
Okay.
Yeah.
You are working on the integration of the transparent contacts for having the actual transparent device?
Yeah, we are working with our collaborator from Professor Aldo Di Carlo group, who is able to have this facility to do sputtering, to combine the transparent contacts and the perovskite absorber. Yeah, I guess he will bring with some discussion.
Okay, thank you very much.
I don't want to say something wrong, but as far as I remember, full devices with the transparent back contact gives AVT at 55%, something like this.
So the contact itself?
No, all the devices with the Spyro and all the devices.
Okay.
Yeah.
Mm-hmm.
Thanks, Brad.